Hello students. Yesterday in my lecture I had done the discussion on close packing structures in one-dimensional, two-dimensional and three-dimensional. And in two-dimensional we studied about square close packing and hexagonal close packing, and in three-dimensional arrangement is studied about the simple cubic structures and hexagonal close packing structures and cubic close packing structures. In that, there are two types of the voids we discussed. One is the tetrahedral void, another one is the octahedral void. Let me recall that the tetrahedral voids are forms. So when we join the three spheres, so this is the arrangement of particles in hexagonal close packing system, where the first layer it is in three particles. There is another one particle is placed on the A type of voids created in first layer, so that empty space is just looks like a tetrahedron. It is in a tetrahedron structure. This is the structure of tetrahedron. So therefore, that empty space is called as tetrahedral. Okay. Similarly, there is another one type of arrangement which forms the octahedral voids. So octahedral voids, for example, octahedral voids are formed by the B type of voids. Okay. This is the B type of voids. Okay. In first layer and in second layer, there are three spheres. Which covers the B type of voids. Okay, when we join the centers of all these spheres, it forms a octahedron. Is the name tetrahedron. And here, when we join the centers of all the spheres, let me put the dots as the centers of spheres. When I join the centers of all the spheres, it forms like an octahedron. So that the space here, that is an octahedral shape. So therefore, that void or that empty space we call it as an octahedron. Okay. Octahedral, and there the shape is octahedron. And since here the particle void ratio also be calculated. There are total n number of particles, so n number of particles will form 2n number of tetrahedral voids and n number of octahedral voids. So there is a formation of voids in close packing structures. Okay. And since the next one, the next concept in solid state, that all we already done the discussion in close packing, and today we are going to discuss about the density of any unit cell. As friends here, density we know, density is defined as mass by a volume. Let me write the density and using the symbol to denote the density as D. So D is equals to is mass by volume is the definition of the density. Okay. Now we are calculating the density of the unit cell. Therefore, I can write this as mass of unit cell by the volume of unit cell. It says here, the mass of unit cell means it is the mass of all the particles present in that unit cell. Okay. The volume of unit cell is the unit cell is a cube. Okay, because we are discussing about the cubic system. So here the unit cell is in a cube. The volume of unit cell, we know it is the length into breadth into height. So where all the length, breadth, heights are same. So if we define the length as an edge length, then the volume of edge length as an A, and the volume of unit cell is equals to A cube. Okay. Let define or let consider. Consider edge length is equals to A. Then the volume of unit cell becomes is A cube. So here let me the volume of unit cell is equals to A cube. And in numerator says the mass of an unit cell. So let me define the mass of each particle, also mass of the particles. Mass of each particle as small m grams. Okay. So mass of a one particle is defined as a small m. If the total number of particles present in that unit cell, the number of particles in the unit cell is defined as a cell. Okay. So here denoting Z as a number of particles. Okay. And number of particles, this value changes with the type of an unit cell. If the unit cell is a simple cubic, then the Z value is 1. If the unit cell is in a BCC, that is a body centered cubic, then the Z value is 2. And in face centered cubic cell, the Z value is 4. We already calculated the number of particles present in these different types of unit cells. Okay. If I multiply the number of particles with the mass of each unit cell, I get the mass of each particle, I get the mass of unit cell. Okay. So here writing the mass of unit cell is equals to, so mass of complete unit cell is number of particles is multiplied with mass of each particle. Okay. Let me substitute these two values in the above equation. That is the volume and the mass of unit cell. Okay. But I will get here. Let me do. So D is equals to is in numerator is Z into small m divided by denominator volume is A cube. For instance, here the Z we can easily calculate. That is by knowing the type of unit cells, we can find the value of Z. And edge length is also calculated by using an X-ray diffraction method, where we can calculate the edge length. By knowing the edge length, we can easily calculate the volume of an unit cell. And another one is the M. So here M is the mass of a particle, mass of each particle. So it is very difficult to find the mass of each particle. Okay. But we can easily calculate the mass of the gram molecular mass of a substance. Okay. For that, let me write this curve notion. The gram molecular mass of any substance. Okay. Right. Let me define that as a capital M. So this is the gram molecular mass of a substance or an atom or a particle is equals to, it contains Avogadro's number of particles. Gram molecular mass of an atom or molecule or ion. So gram molecular mass of that substance is equivalent to Avogadro's number of particles. Okay, Avogadro's number of particles. And this one Avogadro's number of Na of particles. Now, mass of one particle. So Avogadro's number of particles means it is the mass of 6.022 into 10 raised to 23 number. Okay. So the mass of 6.023 into 10 raised to 23 numbers mass, I am defining that as a capital M, that is a gram molecular mass. If mass of one particle is equals to how many grams? Okay. So mass of each particle, there is a small m, mass of each particle is equals to how much? So there is a m gram of particle is equals to how much? Okay, so it is a mass. Okay. So here we calculate it as m is equals to, so m gram of mass particle is equals to, it is the mass of one particle, so 1. Okay. So therefore small m, capital M is equals to is Na divided by therefore here as I told students, m gram mass, that is the mass of each particle, is equals to m gram of mass is equals to, I can write the small m is equals to the total molecular mass divided by Avogadro's number. Okay, that will give me the mass of particles, so mass of each particles. Let me substitute this value in the above equation, that is the d is equals to, it is z into where small m is m divided by Na into AQ. So this is the formula which is used to find the density of a particle. So sorry, density of a unit cell. The density of unit cell equal to Z into capital M divided by Na into AQ, where Z it stands for the type of unit cell. The value of Z it depends on the type of unit cell. If the unit cell is simple cubic, its value is 1. If BCC, its value is 2. If it is FCC, that is a phase center cubic, its value is 4. And capital M is the gram molecular mass of a substance. So gram molecular mass of an atom or a molecule. And Na is the Avogadro's number, and its value, it is 6.023 into 10 raised to 23. And AQ is the volume of unit cell, where A is the edge length. It stands here. In right, for simple cubic cell, the density is equal to, the density is Z is 1 for simple cubic unit cell, therefore the density is defined as m by Na into AQ. And for BCC, the D equal to is 2m by Na into AQ. And similarly for FCC, it is D equal to 4m by Na into AQ. Okay, so just copy these. Next friends, before I start some numericals on this density of unit cells and other parameters what we already discussed, so let me put some, let me show a table in which I am including all the parameters. For example, SCC unit cell, the total number of particles present in SCC unit cell, that is the number of particles in SCC unit cell. So total number of particles in SCC unit cell is 1. Similarly, in BCC unit cell, there is a body centered cubic, the total number of particles are 2. And in face center cubic, the total number of particles are 4. Okay. So these are the parameters. So first parameter, there is the number of particles, and second one is lattice points. Lattice points in SSC there are 8. There are 8 corner particles. In BCC, lattice point is 9, 8 corner and 1 body center. In FCC, 14, 8 corner and 6 face center particles. And third one is about the relationship between A and R. That is the edge length and the radius of sphere. And in simple cubic cell, there the edge length is equals to 2r, or we can write r is equals to a by 2. And in BCC, the edge length a is equals to 4r by root 3, or r equal to root 3 by 4 into a. And in FCC, a is equals to 2r root 2, or r is equals to a by 2 root 2. And next, we calculated the packing efficiency. Packing efficiency in simple cubic cell, 52% of the space is occupied by the particles, and in BCC it is 68%, and in FCC 74% is the packing efficiency. And next parameters, there is the void. So here, this is the space occupied by the particles, and remaining is the empty space. That empty space we call as a void. Okay, so void here is 48% is the empty space in that unit cell, and here the 32% is the empty space in BCC unit cell, and 26% is the empty space in FCC unit cell. And the sixth one parameter, just now we calculated the density. So density D, there is a gram per cubic centimeter. So we express that density in that unit. There is a gram per cubic centimeter. The density D is equals to Z into M by Na into A cube, where Z is 1, so therefore it is M by Na into A cube, and here it is 2M divided by Na into A cube, and here the 4M by Na into A cube. So these are the few parameters. Remember these few parameters that will help you to solve some numericals. Okay, now students, let me solve some numericals. So numericals on formula of a compound, how to find the formula of a compound. And next one is the relationship between the edge length and R and density. So here, there is a first example. Let me read that. A cubic unit cell is made up of the three elements. Elements are X, Y and Z. Here the atoms of the X are present at the corners. X atoms, they are present at the corners. And the atoms of Y at the cube center. And atoms of Z at the center of each face. Then what is the formula of the compound? We know unit cell is a cube. So in cube there are 8 corner particles, 6 base center particles and 1 body center particle is present. And here atoms of X they are present at the corners. Okay. So atoms of X they are present at the corner means that there are totally 8 corners in the cube. So therefore there are 8 X particles are present. 8 X is at corner. There are 8 X corner particles are present. And the contribution of each corner particle. Okay, so when they say these all are the X particles. They are presented at the corners. So contribution of each corner particle, it is 1 by 8. This is the contribution. Contribution of each corner particle is 1 by 8. So after simplifying, we get 8 X into 1 by 8, that is equals to X. Therefore the total number of particles in that unit cell is X. That's 1X. And next the atoms of Y. See, atoms of the Y, they are present at the cube center. These are present at the cube center. That is at the center of this cube. Right? See, body centered or the center of the cube. So let me write this is a y. Okay. So there are only one body center particle is present, therefore the one y, okay, it is at body center, is multiplied with the contribution of body center particle is 1. Okay, so it completely belongs to that unit cell only, therefore the total number of y particles here is 1. And next is the atoms of Z. The atoms of the Z, they are at the center of each phase. Okay. So there are totally 6 phases. All these phases, the Z particles are present. Okay. So there are totally 6 phases. That means there are 6 Z atoms are present. So 6 Z, they are at the phase center. And the contribution of the phase center particle, we know it is 1 by 2. So 1 by 2 is the contribution of each phase center particle. Therefore, after simplifying this, 6 into Z into 1 by 2 is equals to 3Z. So the total number of Z particles in that particular unit cell is 3Z. Therefore, the simple formula, of compound is X, Y and Z raised to 3. This is the simple formula of that compound. They are in the ratio of 1:1:3. So the formula is X, Y, Z 3. Okay, next is second example is also on formula of the compound. Here, let me read that formula example. The cubic unit cell, it consists of 2 elements. Okay, it's a unit cell made up of 2 elements. I'm defining that as P and Q. So here, the atoms of the P, they are present at the corners and the face center. See, atoms, they are occupied by both the positions, corners as well as the face centers. While the Q particles are present on the edge centers and the body center. Right? So if I put the simple Q, and here there are 2 elements P and Q. So P are present at the corners as well as face center. So this means this is the corner particles. They are P, and also the face center. Okay, so the phase center particles are also P. Okay, there are 6 phase center particles. And the Q particles, they are present on the edge center and the body center. So at the body center there is a 1 Q, and also edge center they contain Q particles. So all the edge centers they contain Q. And here students, let me calculate the formula of that compound. First, let me write the total number of P atoms present in that unit cell. Okay. So atoms of P is equals to atoms of P. There are 8 corner P particles. So let me write the 8 corner particles, and contribution of each corner particle is 1 by 8. Along with that, there are face center. They also contain face center particle is also P. So therefore, the 6 face center, and contribution of each face center is 1 by 2. Okay. So therefore, if I simplify, it is 8 into 1 by 8 plus 6 into 1 by 2. So that is equals to 1 plus 3 equal to 4. The total number of P particles are 4. And now the atoms, or the atoms of Q. Atoms of Q is equals to, Q is present at the edge center. Okay, the total number of edges. Okay, just not the edges. So these are the edges. Okay. So in Q, we have totally 12 edges. So yes, is 1, 2, 3, 4. Next 5, 6, 7, 8, 9, 10, 11, 12. There are 12 edges. Okay. So that is equals to 12 edges is multiplied with, and contribution of each edge-centered particle to that particular unit cell is 1 by 4. Is a 1 by 4 is the contribution. And so this edge-centered particle is shared by 4 unit cell. So therefore, so the contribution of that edge-centered particle to that particular unit cell is 1 by 4. And now, plus along with that, along with the edge-centered particles, Q is also present at the body center. Okay, so 1 body center. Okay. Now, the total number of particles is equal to is 12 into 1 by 4 plus 1. So, that is equals to 3 plus 1, that is equals to 4. Okay. So, Q and P, they are in the ratio of 4:4. Okay. Therefore, the formula of compound is equals to is P4Q4, or simply we can write PQ. They are in the ratio of 1:1. So therefore the formula of the compound is PQ. Very good questions. Next is another example. So here this example is based on the relationship between the edge length and the radius of sphere in a unit cell. So let me read that. Silver crystallizes in a FCC unit cell. And edge length of the unit cell is given. Edge length of the unit cell is 409 picometer, and calculate the nearest neighbor distance and radius of a silver. First, let me draw the unit cell, FCC unit cell, and the arrangement of the particles in FCC unit cell. And since here in FCC unit cell, we know that diagonally opposite corner particles and a face center particles, they are in touch with each other. So this is diagonally opposite these are the diagonally opposite corner particles, and there is one face center particles. So they are in touch with each other. Right? So first, the nearest neighbor distance. Nearest neighbor distance means, so the neighbor of this atom is the face center particles. So the distance between these two, and the radius of a sphere. This is the radius of a sphere, R, and this is the radius of second sphere. Okay, here let's calculate the 2R and R. Okay, first let me write the given things. So given is A. A is equals to 409 picometers. This is a unit in which the edge length is expressed, that is the picometer. Okay, 409 picometer, and R is equals to question mark, and also 2R, that is the nearest neighboring distance, is also equals to question. And as we know, the relationship between the edge length and the radius of sphere in FCC unit cell. Okay. In FCC unit cell, the A is equals to is 2R into root 2, or we can write 2R is equals to A by root 2. So 2R is the nearest neighboring distance. So 2R, we can write this as 2R is nothing but it is the nearest neighbor distance. Distance that is equals to question mark. So therefore the 2R is equals to A, substitute the A value is 409 picometers divided by edge length is 409, and root 2 value is 1.414 is equals to, so therefore the 2R is equals to 289.25 picometers. Okay. So this is the nearest neighboring distance. Now calculate the radius. Radius is the R is equals to that is Just now we calculated 2R value, and R value is R equal to 289.25 divided by 2, that is equals to 144.625 picometers. This is the radius. Okay, just write instructions. Next example, friends. Let me read them. Sodium crystallizes in BCC unit cell with edge length 4.29 angstrom. What is the radius of a sodium atom, and what is the length of body diagonal of the unit cell? Here, the sodium, it crystallizes in BCC unit cell. We know the arrangement of the particles in a BCC unit cell is, in BCC unit cell, it contains 8 corner particles and 1 is at the body center. And the body center particle and the diagonally opposite corner particles, they are in touch with each other. This is the arrangement of the particles in BCC. And this is the arrangement of sodium atom, so sodium particles in BCC unit cell. So here the question is to calculate the radius of a sodium atom. There is a R is equals to question mark. There is a radius is defined as R is equals to question mark. And another one is, what is the length of body diagonal? This we call as a length of body diagonal. Okay. So this length of body diagonal is obtained by joining the radius of these 3 spheres. This is the length. Okay. The length of body diagonal, it is nothing but sum of a radius of 3 spheres, right? The length of body diagonal is equals to 4R. Is the radius of first sphere is R, and the second one diameter is 2R, and third is R. So therefore length of body diagonal is equals to 4R, and given the edge length of that unit cell is 4.29 angstrom units. Now write the relationship between the A and R for BCC unit cell. In BCC unit cell, we know the relationship between the edge length and the radius of sphere. There is A is equals to 4R by root 3, or it can be written as R is equals to root 3 by 4 into A. When edge length is given, we use this formula. When the radius is given, we use this formula to calculate the edge length. Okay. So here the edge length is given, told to find the radius. So therefore use this second formula. So first let me calculate the radius of an sodium atom. R is equals to root 3 by 4 into A. So that is equals to root 3 value in 1.73 divided by 4 into edge length. Edge length is 4.29 angstrom units. Right. So simplify this, you get R value as R value is equals to is 1.86 angstroms. So this is the value of R. Similarly, calculate the length of body diagonal. Length of body diagonal, that is equals to 4R. Let's simply multiply 4 with the radius of sphere. That is the 4 into 1.86. So that is equals to 7.44 angstroms. This is the length of body diagonal. These are the simple examples which were asked in CET. So it is asked once in CET, what is the length of body diagonal? Just copy it.